Okay, thank you all for coming early on the morning after the banquet. I'm going to tell you about some conjectures which India is really interwoven through this story. So this is my third trip to India. On my second trip, it was 4 years ago, I was here in ICTS, and these conjectures were born in discussions there with Chris Hoffman, Leo Rolla, Vladas Sidrovicius, Deepak, and Tridib. And so that's the origin of the conjectures I'm going to tell you about. And in some sense, they have a prehistory that goes back even further. So on my first trip to India, 2008, this was right after my PhD. I was obsessed with traveling and also with sand piles. And so I decided to combine those obsessions by traveling in India. I invited myself to visit Deepak, and he was gracious enough to host me at the IFR for a couple of weeks. And at the time, I had several conjectures about the abelian sand pile model, all of which turned out to be wrong. And the story of figuring out that they were wrong led to a lot of interesting mathematics over the next several years. But ultimately, I decided maybe there's a different model where those conjectures are actually right. And activated random walk is the best candidate for such a model. So let me tell you how this particle system works. So there are two species of particles. They're active particles, which I'll denote A, and sleeping particles, I'll denote S. And these particles are walking around on a graph or lattice. For this talk, I'll assume everything takes place on the d-dimensional integer lattice. So you have some particles, and active particles can fall asleep. This happens at some rate lambda. Lambda is a parameter which we will play with. The second transition that can happen is that if an active particle jumps on top of a sleeping particle, the sleeping particle wakes up. So A plus S transitions to 2A. And this happens instantly. And the final transition is random walk. So an active particle jumps to a random nearest neighbor. At rate 1. Okay, so these are the laws of physics in our toy universe. You have two types of particles. The active ones do random walks. They fall asleep at some fixed rate, and they get woken up by other active ones when the active one jumps on top of the sleeper. So I've illustrated this here in one dimension. So this is the spatial dimension Z. I started with 3 active particles at one site, and the time evolution of the system is going downward. So, first one of the active ones takes a jump to the right, then it falls asleep there. Then another active one jumps to the left, jumps to the left again. Then this active one jumps to the right, and it wakes up this sleeper. So now we have 2 active particles where this sleeper was. And maybe one of these active ones jumps back to the left, and then these 3 active ones all fall asleep. And here we have an absorbing state. Everything is asleep. So the system doesn't evolve any further, absorbing. boundary condition, good. So now that we have the physics of our toy universe, I want to talk about several different experiments you can do in this universe, starting with the point source with no boundary condition. So let me talk about, say, 5 experiments you can do. Point source. I'll list the experiments so you can see what's coming. Multiple sources. Stationary ergodic. The wired Markov chain. And the free Markov chain. These 3 experiments take place in the infinite graph ZD. These 2 experiments take place in a finite subset of ZD. For example, a big box. And the boundary conditions are different for wired and free. So wired, you can fall off the edge of this finite piece, and in free, you delete the edges leading outside, so V is a closed system. So I'll tell you some conjectures about each of these experiments and how they relate to each other. Point source. I start with this one because it's kind of the simplest initial condition. You have some large number of particles at the origin in ZD. They're all active, and they're going to do these random walks and fall asleep until reaching an absorbing state. I'll denote that absorbing state with a capital S. You could think of S as standing for stabilize. So you start your N active particles here at the origin, and they do a lot of, there's a lot of activity, but eventually they will each find a site to fall asleep at, and there will be no more active particles. The question is, where do these N particles fall asleep? How far do they spread? Here's a conjecture about that. So there exists a number which I'll call zeta A. You could think of it as a kind of critical density. There will be several critical densities in the talk. The A stands for aggregation. We're making a big aggregate of N sleeping particles. It depends on the dimension and the sleep rate. Some real number such that with high probability, so with probability tending to 1, as N goes to infinity. So we're going to bound this, this aggregate between 2 balls. So you have an inner ball and an outer ball. So for the inner ball, we'll say every site in, say, ZD intersect 1 minus epsilon B is visited at least once. And no sites outside 1 plus epsilon b are visited. And what is this b? So in this picture, this is 1 minus epsilon b, and this bigger ball is 1 plus epsilon b. So this guy is the origin-centered Euclidean ball. Of volume n divided by this number zeta a. Okay, so what is this saying? It's saying there's some rotational symmetry of the, at the macroscopic scale. That even though you live on a square lattice, your final aggregate will be roughly spherical. What makes this tricky to prove? Well, first of all, it's false in a lot of related models, including the abelian sand file. And the reason it's false in those models has to do with some inhomogeneity. So what we think is that this aggregate is very homogeneous. Somehow it looks the same everywhere. Everywhere you look, you see the same local density, this number zeta a. And your enemy in proving this conjecture is clumps. So you want to rule out somehow that there are pieces of the aggregate that are macroscopically denser than other pieces. I want to make more precise that homogeneity, but I'll pause for questions about the setup. Yes?
What is epsilon?
Epsilon is arbitrary. So there exists this thing such that for any epsilon greater than 0, this holds. So no matter how small you make the gap between these balls at the macroscopic scale, this will hold with probability 10 to 1.
So is the model anyhow related to the branching random walk or branching Brownian motion with the rate of branching given by the density of S?
Is the model related to branching random walk? Well,
every time it hits the sleeping, it creates 2 branches. And
yeah.
Then the rate of branching is given by the concentration of S.
Yeah. So morally, a lot of these models have some, they're somehow like a branching process, right? So when you have low density, then you have a low rate of active particles waking up sleeping particles. And so activity tends to die out. And when you have high density, you have a higher rate, so your branching tends to persist. But I don't know a rigorous connection between the 2 models.
There is some Monte Carlo evidence you have in favor of these conjectures. Can you show some pictures?
Yes, so I like to show pictures in my talk, but I decided not to show pictures today for the reason that the pictures are boring. So somehow the statement, like this conjecture and the ones following it, are somehow, they're kind of like null hypotheses. They're saying this model doesn't do anything interesting. And the hard part is to prove that it doesn't, right? So, it's, if you make a picture of this, at macroscopic scale, you will see like a perfectly circular blob. And well, what's somewhat more interesting, which could use a picture, is the microscopic scale. So let me talk about that next, if there are no more questions. Yes?
So if you change the rate of a plus a as going to 2a and make it finite, does the problem change?
Yeah. Yeah, so you could make this a finite rate. Yeah, actually, this wouldn't change the problem because, so So there's something I haven't told you about, which is familiar if you know about sand piles, which is an abelian property. So abelian property says that I don't have to worry about which of these transitions happen in what order. So I can, in advance, I can sample like a list of instructions for each site. So the instructions might say, the first time a particle comes here, it should fall asleep. The second time, it should jump to the right. The third time, it should fall asleep, and so on. And I fix those random instructions in advance. And then I can do my transitions in any order, and I'll get the same final stabilization. So if you change this rate to something finite, you will delay the time when you reach that final stabilization, but you won't change what the final state is.
One question about, do you have like any control on like the fluctuations of the spikes of this blob? Like, like probably large deviations of like the furthest person from the origin or something like that?
Yeah, good. So if we could prove this, rotational symmetry, then the next natural question is the fluctuations. And the only situation when we understand the fluctuations is the case when you take this sleep rate to infinity. So maybe I'll mention. So this model has a special name. Internal DLA is the case. Lambda is infinite. You might know DLA as the model which forms these fractal branching patterns. When you have particles sticking to a cluster, they walk from the outside and they stick. Internal DLA is a kind of spatial inversion of it, when you have your cluster, but your particles start inside the cluster and they walk to the edge and they stick. So if you think your particles are falling asleep instantly, if lambda is infinite. And so essentially you just get the model where each particle does a random walk until it finds an unoccupied site, and then it falls asleep there and stays forever. In this case, we have a very good understanding. The conjecture is true, and we understand the fluctuations also. They're very small. They're only logarithmic in the radius. Whether they are still so small for finite lambda is an open question.
Do you have like any kind of evidence that spikes don't develop in the ball?
Yeah, so it seems like spikes don't develop. The boundary is quite smooth. And again, we can prove that in the infinite sleep rate case. Another question?
Your conjecture is about, visited sites. And so I wonder, for instance, when they all fall asleep, so all was visited at least once. But is there still there is some sort of also rotational, probably invariant, but also some decay of density, especially in dimensions higher than one? Is it some simple function how they?
Yeah, good. So the question is like, what does the aggregate look like? If, where are the sleeping particles? So the conjecture is it's completely uniform. So it has local density, the same number zeta A everywhere. There's no decay. And let me write a kind of precise conjecture related to that about the microstructure of the aggregate.
One quick question. So did you say it's abelian? This, you can interchange these?
It's abelian, yes.
Okay.
Yes. Okay. Microstructure. So for each n, we can let's say, mu and v V. Just say mu n. Let mu n be the law of this final absorbing state. Then I can look at what this state looks like on a finite window. So say mu n v is the law of this state restricted to a finite set v. V in ZB finite. So the conjecture is there exists a limit of these measures. So is this a measure U? It takes, so it's a measure on configurations of sleeping particles in the infinite lattice ZB. Okay, such that mu n v converges to mu. So what is the sense of this limit? So the sense is you can ask zero S. Yeah. So there are no active particles in this measure, only sleeping ones, because we're trying to describe the microstructure of this aggregate. The aggregate has no active particles. So the pictures, you have this big aggregate and you're looking at a small piece of it near the origin. And you want to see where did the sleepers end up. And conjecture is as you take n to infinity, so you're making your aggregate bigger and bigger, but your finite piece is fixed. Then the probability law of what you see in this finite window has a limit. Now, you might think the origin has a special role here because that's where your particles started. But conjecture that this limit is invariant under translations of ZD. And it's universal in the following sense. So let me talk about the second experiment, multiple sources. So instead of starting all your particles at the origin, let's start a bunch of active particles in a big cluster. So I'll start with a nice open set in RD, bounded, open, and I won't specify what nice means. And then I'll start with take this set, intersect with a fine mesh, and take one active particle. At each site. And then I want to stabilize that. So maybe this is what my set A looks like. I fill it up with active particles. And now I want to stabilize it. And these active particles, well, they're trying to fall asleep. And they have trouble falling asleep until they spread out far enough. So they will spread out to fill some larger region of the lattice. And we'd like to know what region is that. So this is the initial condition. You have this dense clump of active particles. And then the final configuration, there will be some bigger set where your sleeping particles land. And they will land in, conjecturally, they will land in this larger set, which I'll call A star. So the conjecture is that when you stabilize this cluster, you'll converge in weak star to this same density, zeta A, times the indicator of this larger set, A star. And what is A star? So A star is the unique up to measure 0 set satisfying a certain set of inequalities. The inequalities look like this. If you take a superharmonic function and you integrate it over the original set A, that should always be larger than if you integrate the same superharmonic function over A star and scale by zeta A. So this is for all integrable superharmonic functions on A star. Okay, this might look sort of mysterious. It's like a very indirect way to characterize what the domain is. You know, we're not giving you a formula for the the boundary of A star or anything. What we're doing is we're specifying this infinite family of inequalities that for any superharmonic function, when you integrate it over A, that's bigger than zeta A times its integral over A star. And well, it might not be obvious, but these inequalities are enough to characterize the domain A star up to measure 0.
At least A star is bigger than A?
It's bigger than A.
Always?
Yeah.
Bigger than, equal to, or bigger than?
Okay, this is a great question. Is A star strictly bigger than A? So that has to do with the question of whether this number is strictly less than 1. And there have been a lot of recent progress on questions like that, that a different critical density is in fact strictly less than 1.
No, if
So-
it is not bigger than, if it is strictly bigger than A, then these two things will not be consistent. Because if you start there and you reach like in a sleepy state, and then you initiate all sleepers as active, and then you again apply that. So you have the same density again, because number of particles are not changing. So if you do repeatedly, it cannot become bigger, because the area becoming bigger and the number of particles remaining same, the density cannot remain same.
Right, so clearly the particles will spread out a little bit, right? The question is, do they spread out macroscopically? And the conjecture is yes. So conjecturally, A star is strictly bigger than A. And there's some progress in this direction, which I will tell you about if I have time. But let me first just give you some intuition for like where this set of inequalities comes from. Physically, this is what you get in a version of what's called Healy-Shaw flow. So you have, imagine a blob of fluid that's trapped between two plates. And what you can do, so there's, let's say, a 1 millimeter gap between these two plates. And you've got a blob of fluid in the shape of your set A. And now you squeeze these two plates together so that that 1 millimeter shrinks to this, to only zeta A millimeters. And your blob, you know, by kind of conservation of, it's an incompressible fluid, say. So by conservation, your blob has to spread out. And the shape that it will make when you've narrowed the gap between your plates is A star. Yes? The Laplacian negative. Negative, yeah. Yes. This just means Laplacian negative, and a technicality is that you need to consider this in a weak sense, a viscosity sense, so that you have enough superharmonic functions. Okay, so that's the macro structure that describes like where your particles end up, and the microstructure should be the same. So in this setup, so conjecture for the multiple source so if you take this other condition, indicator of A intersect the lattice, stabilize, restrict to this finite window V. It has the same limit, the same. So no matter how your particles were macroscopically arranged, when you stabilize them and you look at a tiny piece of the aggregate, it looks the same. It doesn't see the macroscopic structure. Okay. I only have time to tell you about one more conjecture. That's the wired Markov chain. So these experiments I told you so far were in the infinite ZD. But then we restricted them to a finite window, this V. And so you could ask, well, what happens if we just restrict to V from the beginning and put open boundary conditions? So your particles that exit V are removed from the system. So that gives you a Markov chain on a finite state space. Wired Markov chain. This is experiment 3. So you could think of, I will finish with this conjecture. You could think of V as, for example, a large ball. Intersect with the lattice. And so the Markov chain, it's a discrete time process with state space, all configurations of sleepers on this finite set V. And the transition is to add one active particle and stabilize. So at time t plus 1, you take the configuration at time t. Let's say add a single active particle at some random site ut, and then stabilize. Add one active particle. Stabilize. So this chain captures the kind of avalanche nature of the model, that everybody is asleep. I drop a single active particle and maybe it falls asleep, but maybe it wakes up some sleeping particles and those particles wander and they wake up more particles and you get a big avalanche. So what we'd like to describe is the stationary distribution of this Markov chain. We know some interesting things about it, which I won't write down for lack of time, but we have a way to exactly sample from the stationary distribution of this Markov chain, which suggests that there could be, some actual formulas, but we don't have formulas for it. I have a bunch of conjectures about it, which I'll just state one of them, which is that the stationary distribution so that depends on your finite set V has an infinite volume limit. As V increases to VD. So the limit is a measure on, again, it's a measure on spatially infinite configurations of sleepers. And well, it's interesting to speculate, how is this limit related to the first conjectured limit? I don't know if they're equal, but I would conjecture that they have the same density. So this zeta A that featured in the aggregation experiments is equal to the expected value under pi. Right, so this expected value is just saying you sample from this infinite volume stationary measure and you look, what's the probability that there's a sleeper at the origin? And the conjecture is that that probability is the same as this zeta A. And sort of a more bold conjecture, which I don't necessarily believe, so I'll just phrase it as a question. Is pi equal to mu? So are these two infinite volume measures the same? Okay, I have more to say, but no more time. So I want to thank you all for the invitation, and thank you, Deepak, for inspiring so much of my work.
Thank you, Lionel, for such a very intriguing talk. Yes, Sanjib.
This model, if you take it in a finite volume with a periodic boundary condition, so I guess as a function of density, it will have a active to sleeping transition, right?
Yes.
Have you checked, and what is the order of the transition?
Yeah, good. So this was experiment 5 on my list, so I didn't get to it, but the free Markov chain is the one where you don't allow your particles to exit the system. And here, well, if you have fewer particles than the number of sites, then eventually, if you wait long enough, they will all fall asleep. Now, there is a phase transition between fast and slow. So if you're at low density, they will fall asleep quickly. Like each particle will take only order 1 step. And if you're at high density, then they will fall asleep slowly. In fact, it's proved now in the case of a cycle that for high enough density, it will take exponential time to stabilize. So you can ask, what's the, where is this transition between fast and slow? And conjecturally, it happens at the same place, the same zeta A.
Active particle in the active state as a function of density, how does it increases?
Yeah, so it would be very interesting to find, avalanche exponents and so on for these models as you approach the critical density. And maybe they are simple rational numbers, and Deepak can tell us what they are.
Hello, Ne. Okay. I have a very short question, 1 or 2 short questions. Totally in the initial definition of your thing, when you added n particles at a site and there is a lambda rate active to sleep. So how the number of active particles decay with time? So I don't know whether you have covered this or not. So that I am interested to know. And also at the end, you said that there is a distribution of sleep particles. Everybody is sleeping and you are adding 1 particle. I don't know the avalanche is, then it will be, there will be activity and again it will be sleeping. Okay, after some time it will be sleeping. So you can measure the number of movements and you can call it an avalanche. And this avalanche will occur even if you make open boundary system or closed boundary. In both cases that will occur. So if you have any insight to that, and if you'd like to comment.
Yeah, so good. So the first question was about the decay of the number of active particles in time. Yeah, so, well, 2 comments. One, I don't like this kind of question because it kind of breaks the abelian property, right? It forces you to choose a particular time evolution, okay? But putting that aside, yes, I think, so there should be a smooth decay of the number of active particles. But it will be like, it will always be a constant fraction of them. So there'll be a macroscopic proportion of active particles until the very end. So yeah, it would be interesting to try to conjecture a formula for that. Yeah, it's not exponential decay. So there are a lot of active particles until the very end. Yeah, your second question about the avalanches, like, we would all like to understand the avalanches better. Somehow, I think we're not ready, at least as mathematicians, we're not ready to even address those questions because we don't understand like the stationary state. So the stationary state is very mysterious. One property of it that I didn't get to write down in my conjecture is hyperuniformity. So we believe that the sleepers they're very kind of evenly spread out. So if you look at the variance of the number of sleepers in a given volume, it scales like a power of the volume less than 1. So somehow these sleeping particles, they really fall asleep in, they kind of repel each other. So they fall asleep as far apart from each other as possible. And I think understanding that would be a first step toward understanding avalanches.
Sorry, one question. If you take the lambda goes to 0 limit, that seems more tractable.
Yeah.
In particular, this zeta will go like lambda to the power half small lambda, and then can you discuss that limit in more detail?
Yeah, that's right. So there's several recent works that prove just what you said, that the zeta is like square root of lambda as lambda goes to 0. But we don't have the constant in front of the square root. So yeah, I mean, maybe that limit is more understandable than the general case. But you know, we need the constant to get anywhere with it.
Okay, next question, Punya.
Hi. So your zeta A, I mean the macroscopic stabilized density and the fixed energy sand pile critical density zeta C. I mean, are they same, or I mean it's a conjecture, or?
Yeah. Well, okay. For the fixed energy sand pile, this model was kind of inspired by the Mana sand pile. We'll hear from Mana very soon. But the densities aren't going to be the same.
Mm-hmm.
You might hope, though, that things like avalanche exponents for activated random walk would also apply to a wider class of abelian networks, including the Mana sand pile.
No, I mean, you rule out that they are not same, or they may not be same. I mean,
in experiments, they're not the same.
Oh, I see. Okay, thanks.
Next question, Abhishek.
Yeah, so sort of similar question to Deepak. I mean, so supposing I decrease this rate lambda as some 1 by n to the power, some power. So is there some critic like A where you get some non-trivial?
Yeah, good. I like that question. So you could take lambda scaling somehow with n. One work in progress with my PhD student Hannah Cairns and with Shishendu Ganguly, we looked at in one dimension on a cycle. We looked at a completely full configuration. So there are n particles on an n cycle. So it's very hard for it to stabilize. But then we take lambda quite large. So they're very prone to fall asleep, and ask what is the right scaling of lambda. And so it turns out to be 1/2 log n. So when lambda is constant log n for c bigger than 1/2, then you fall asleep quickly. And when it's constant log n for c less than 1/2, you take exponential. Well, you take a long time to fall asleep. So we can also do this in higher dimensions, but somehow one dimension is the most interesting because you get the log.
Okay, for the sake of time, we'll move to the next talk now. So thank you, Lionel, for the nice talk.